Molecular polarity. Molecules in which the electrons are not evenly distributed experience a negatively and positively charged pole when in an electric field and are said to be polar. The strength of the poles is known as the dipole moment. Two factors contribute to the polarity of a molecule. Polarity of bonds, remember, polarity of bonds is determined by the electronegativity difference of the two atoms involved in the bond. Polar bonds are necessary for a molecule to be polar, but do not guarantee polarity. What that means is you need to have polar bonds, but that is not the only condition necessary for a molecule to be polar. Second is symmetry. To be polar, a molecule must be asymmetrical to ensure an uneven distribution of electrons. In general, symmetry is defined by the Vesper number. A Vesper number ending in 0 is usually, but not always, symmetrical. Any Vesper number ending not in 0, with the exception of 642, will be asymmetrical. Certain shapes are asymmetrical in nature due to unbonded electrons, as we said. All Vesper numbers not ending in 0 and 642. Therefore, they result in polar molecules. So any of the shapes listed here, bent, trigonal, pyramidal, T-shape, seesaw, square, pyramidal, are asymmetrical. So that means that so long as you have polar bonds within any of those shapes, then your molecule will necessarily also be polar. Asymmetry and polarity can also result from a heterogeneous group of atoms attached to a central atom, thereby creating asymmetrical differences in electronegativity. Let's look at CHCl3 for an example. CHCl3 has a shape of 440. However, it is not symmetrical because you don't have the same atoms surrounding the central atom, and the electronegativities between carbon and hydrogen and carbon and chlorine are different. In fact, carbon-hydrogen is considered a non-polar bond. Therefore, even though it has a shape of 440, it is not symmetrical, and therefore this would be a polar molecule. Now, if the molecule is asymmetrical, the more polar the bonds, the more polar the molecule. We look at water, which has an electronegativity difference of 1.4. The dipole moment is 1.85. Whereas you look at hydrogen sulfide, which has an electronegativity difference of 0.4, the dipole moment is only 0.97. Both molecules are asymmetrical and exhibit a dipole moment, but water's dipole moment is significantly higher than hydrogen sulfide because of the greater electronegativity between oxygen and hydrogen.